the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
So I'll just briefly introduce myself and give you my background. As you were told, I'm a Stevens alumni. I started my undergraduate in 2005 and graduated my undergraduate in 2009 in environmental engineering. At the time I was getting ready to graduate, I started doing some job interviews, mostly brownfield remediation sites, wastewater treatment facilities, which is what I was looking at the time based off what my degree was focused on. At that time I actually did an internship with EPA over that summer with one of their remediation teams. Basically we would go do low flow well testing, test basically underground sources of water for contaminants. And it was a great experience, but just didn't strike me as what I wanted to do with my career. So I was always a fan of fluids, and basically, as an undergraduate, fluids is restricted to pipe flow, and it's fairly straightforward, to get your hands around. So I decided, since I love the ocean, I've always, enjoyed going to the beach, and found, even from a spiritual standpoint, the ocean is very calming and peaceful. So I decided that I wanted to extend my studies to learn how hydrodynamically the differences between, when you have, stream flow, pipe flow, and fluids versus an active dynamic system, which is constantly changing, has endless parameters that are affecting it. And I started my master's in 2009, finished it in 2010, at which point I decided that I wanted to continue my career in academics. Everything about it I enjoy. I like working at the university. I enjoy the act of research and the idea that you're basically encouraged to develop new ideas to bring to not only the marketplace but just to academia really struck me as something interesting. I was always sort of like a big ideas guy, and the fact that you could create your own PhD dissertation based on your own interests really struck me as interesting. So I decided to do my PhD. So I call it the trilogy. I did undergraduate, master's, and PhD. Typically, if you knew you wanted to do your PhD early on, people would advise that you do it at different universities. So you basically get exposed to different people and their experience. But actually, it was never my intent to do my PhD. So I was just sort of going with the flow, and at the time, it just ended up being what I wanted to do, and it's worked out very well. Actually, the advisors on my PhD committee, so every PhD, these 5 advisors, some internal to Stevens and some exterior. One of them was actually the founder of ECOncrete. So ECOncrete is actually a company originally based in Tel Aviv in Israel, and the 2 founders, Dr. Shimmer Perko-Finkel and Dr. Ido Sella, they're marine biologists, and in their previous life they used to do underwater surveys of marine organisms. So they wrote offshore oil platforms, all sorts of structures, marinas, ports, and they would evaluate the growth, and they would survey the wildlife, the biodiversity, the different species that could be expected. As they were doing these different tests, they saw different materials recruited different organisms better or worse than others. So one day they came across this concrete structure that was had substantially more growth than any other concrete unit they've seen in the water before. So they started to look into that, and they started basically tweaking what you call concrete admixtures. So, you know, when you make concrete, you have your cement content, you have water, you have aggregate, which is your stone, and you put that all together and ultimately you have concrete. But as concrete technologies have advanced, this idea of an admixture is basically a small content of the mix is replaced with higher quality materials that are intended to improve the mixture, either make it stronger, make it cure faster, make it cure underwater. Depending on its intent, there's hundreds, if not more, different admixtures out there currently on the market. So what they did was ultimately they identified 5 different recipes or admixtures that promoted biology more effectively than Portland cement. So we'll get into the benefits and disadvantages of Portland cement versus our concrete as we get into the presentation. But you know, I guess that's really all I want to say is for myself as far as an introduction to this point. I guess the only thing to mention is my actual PhD is focused on what we call environmental engineering. So I started off early on just as a traditional postal engineer, but considering I had my environmental background, luckily the advisor I had at the time encouraged me to sort of combine the two. The concept of living shorelines is basically to stabilize shorelines, stop erosion, have coastal defense that not only performs structurally but also speaks to the diverse habitats that are normally in the coastal zone. So that's really where I found my niche, and you know, ever since I've been working in that field, and you know, just truly enjoy it. Learned how to scuba dive along the way, learned how to surf. You know, really tried to make a lifestyle out of it. So as I said earlier, it worked out pretty well for myself. We'll get now into the bulk of the conversation, or the presentation rather. So I'm actually going to take off my webcam screen, full screen. And I think before I even start the presentation, I wanted to show you this 2-minute video that should give you a decent background of what we do before I go into more finer detail.
ECOncrete brings urban and coastal concrete infrastructures to life using proprietary bio-enhanced concrete. 2/3 of the world population concentrated around coastlines, exposed to ever-increasing extreme weather events and rising sea levels. Accelerated coastal development is inevitable, creating tremendous pressure on marine ecosystems. 70% of coastal infrastructure is concrete-based. Our science-based concrete compositions, textures, and designs enhance the biological performance and ecological value of concrete structures, while increasing their durability and lifespan. ECOncrete provides services from A to Z, from site analysis, concepts and design, through product supply, to project monitoring. Our technologies can be applied as ready-to-use precast products or by using our unique forms alongside our bio-enhancing admixtures. The company's line of precast products currently includes ecological armoring units, enhanced seawalls, design tide pools, and articulated concrete marine mattresses. Our forms, liners, and admixtures can be used for on-site casting of new elements or for retrofitting structures like pier piles. These can also be used by licensed partners at their home facility. All our products are tailored to encourage growth of diverse plants and animals, such as oysters and corals, which build calcitic skeletons on the concrete, in a process called bioprotection. This calcitic layer encases the concrete, contributing to the strength and stability of the structure. Our patented bioenhancing admixtures have been fully tested in a variety of marine ecosystems across the globe, yielding excellent results. We have succeeded in creating a win-win solution for both thriving ecosystems and high-performance concrete structures. The scientists and professionals at ECOncrete are proud to be at the forefront of the next generation of ecological engineers, and we invite you to join us.
Okay. So that I like starting with that just because it gives you a general background in case you've got the presentation and sort of a great start to introduce our technologies and how we try to implement them into coastal infrastructure projects. So getting right into it, ultimately the population of the planet has increased exponentially, especially over the last 100 years or so. And a lot of those populations, actually more than 70%, are focused within 100 kilometers of the coastline. With that high presence or high population, there comes basically these stressors on the shorelines, where there's pressure to keep water out, to stop erosion, to protect the land where it is, where historically civilizations or different cities weren't located so close to the ocean, or you wouldn't have homes typically on barrier islands like we see in New Jersey. Really, we've exposed ourselves to vulnerabilities by creating infrastructure, homes, utilities so close to the shoreline. So ultimately, we've been forced through what the term would be harden the shoreline, and along with that hardening, unfortunately, there's been a significant loss of habitat, species biodiversity, species abundance. Ultimately, what we have done is we've taken the intertidal zone, which in a natural environment in the intertidal zone is anywhere between your high water and your low water within the daily tidal range. And that's the most, like I said, in a natural setting, the most diverse and abundant place for these species to develop, because there's the most sunlight, there's the most nutrients, there's higher flow rates along the surface, so there's better circulation, so you can clean the water better. It's just, all in all, more than 90% of the species that grow prefer to grow in the intertidal zone itself. But over time, we've replaced all these natural settings with vertical concrete structures, wooden structures. And here we see that more than 60%, or actually more than 70% of coastal infrastructure is concrete-based. There's lots of reasons for that. Basically, concrete was invented in ancient times by the Romans, especially the concrete that especially for setting in water. They developed basically, I mentioned earlier admixture. Basically, they added in different ash materials, volcanic ashes, into the cement that actually allowed it to cure underwater and to dry and get stronger over time. So concrete is an extremely useful product. If you're in an environment like in the Mediterranean or in Israel, you see these large units here on the bottom. Those are antifers, armoring units. Basically, there's dozens and dozens of these different proprietary units, and they're popular in that region of the world because actually they don't have stones large enough to combat the wave from erosion that they're exposed to. So during winter conditions, you can see anything waves from 20 to 30 feet are typical along some of these shorelines. So there's not enough natural stone that's large enough to mitigate that impact. So ultimately, they make precast units. However, from a biological standpoint, concrete basically is a completely sterile surface. So you see in the bottom right picture, that's in the Mediterranean, one of the most species, one of the most abundant ecosystems in the world. And this concrete sinker is based on Portland cement, which is the most widely used cement in the world. Has, you can see, really 2 to 5% coverage of organisms. And you can see if you go next to it, If there is an abundance of organisms, it's typically invasive species. So this picture is from the Great Lakes, freshwater. Ultimately, these species were introduced to the Great Lakes through the ballasts of ships. And once they were introduced into that environment, they basically took over, and again, they're ruining the biodiversity. They're killing off more sensitive species, and we're seeing entire ecosystems change. Also, to concrete, you see on the top, as I said earlier, is created traditionally in these vertical forms, right? So say in New York, the tidal range is 4.5 to 5 feet. So your tidal range is literally restricted to that vertical distance of 5 feet, right? It travels up the wall, tide point, travels down the wall 5 feet to the low point. However, if you look at the picture next to it, in this natural shore zone, same tidal difference, 5 feet, but actually it's allowed to occur and impact hundreds of feet of the shoreline due to the mild sloping shores. So what we like to do at ECOncrete is basically we modify the composition of the concrete itself with our admixtures. You can run it away a bit for me. So we modify the composition with our admixtures. So Portland cement has a pH of 12.5 to 13. It's extremely basic, and that's one of the major reasons why these organisms can't populate its surface. So there's plenty of natural larvae and naturally occurring organisms in the water, and if there's actually substrates that were more natural to them, they would occupy them. However, since we're using concrete, there's a lot of chemicals that actually leak out of concrete over its lifetime. There's just a lot of negative components in it. Often, even the mold release. So sometimes in these units, they use all sorts of oils and just really not environmentally friendly materials. So what we do is we replace anything that's negative with something that could be positive for biology. So we actually, for our mold release, and you can imagine it that if you're cooking or you want to spray oil on your pan, it depends which oil you use, whether you're using virgin olive oil versus coconut oil. Just how it affects your food, it affects the chemistry of the concrete. So we actually use the vegetable-based form release for our products. Besides the composition, we also add texture, both on the micro and macro scale. So if you see in these pictures here, there's small nooks and crannies and holes. These are all very deliberate. So if you have a smooth surface, the organisms that could potentially populate that surface have nowhere to hide. There's no refuge, so they're exposed to the full force of wakes and currents. And ultimately, the more juvenile and sensitive their species can't develop on these surfaces. What we do is we make intricacies within the surface, and like I said, both on a micro scale, so you can see these very, very fine texture patterns. To the macro scale, if you look to the unit to the left, that's a water retaining feature. It actually serves to capture water during periods of high tide, so that when it's low tide, biology can continue to develop. But the benefit, and here you can see, just to speak again to what I was just saying, we take basically a three-pronged approach: composition, texture, and design. But the benefit really is, of course, you get ecological uplift of your system, so you're promoting the development of these organisms on your structure. So as far as a structural standpoint, our concrete has no limitation. We can make it to any strength, we can meet any specification that any contractor or project would like us to meet. However, it comes with this advanced development of biological organisms, which actually serves to make the concrete stronger over time. So you see along the top right, this is from a study from Louisiana State University, and ultimately they put the concrete units in the water, and just purely by the presence of oysters, within 2 years, they were able to increase its strength tenfold. Now, the reason this happens is because oysters, mussels, barnacles, corals, these are all calcium carbonate-based organisms. And calcium carbonate is basically a natural form of cement. So what is happening is, over time, the entire structure is becoming encased with these organisms. Not only is increasing its strength and carrying capacity, but creating a buffer between the environment and the actual concrete unit itself. So these organisms will absorb the wave action, they absorb currents, if there's any forces from floating debris. Say you have a huge, massive storm and a lot of these organisms are wiped out, they're completely resilient and they rebound on their own. So we're actually reducing maintenance and increasing lifespan of the project. So not only do we have the ecological and biological advantages, but from a structural standpoint, we're also having a superior product. So I'm going to start to pick up the pace a little bit here just because I'm aware of the time restriction for today. But when the company started in 2011, we ultimately had to evaluate our products, right? So we did this both in a lab setting and in the field. So we looked at ECOncrete mixes, 5 different ECOncrete mixes versus standard Portland cement. And we looked at both textured and smooth surfaces. And ultimately we evaluated it around the world. In the Red Sea, the Mediterranean, the Great Lakes, which was freshwater, Governor's Island, Brooklyn Navy Yard, Savannah, Georgia, and the Florida Keys. And ultimately, a lot of the findings that we found in this study, you're going to see repeated throughout the presentation with all of our projects. But ultimately, we were able to increase biology in every case versus the Portland cement. So here, this is looking at some of our lab experiments. We looked at 3 different types of species in the labs. And you can see Portland cement is the last bar on the bar graph. So in every scenario, every mix, no matter what the environment was, even though we now know which mixture is most appropriate for which environments, they would still outperform Portland cement in every case. And then we also looked at oysters. This was specifically working with the group at Governor's Island. I don't know if you guys are aware, but there's a very large movement to restore oysters to New York Harbor. New York actually used to be the oyster capital of the world, and over 99% of that oyster population has now become extinct through pollution, over-harvesting in the early 20th century, and ultimately, there used to be 350 square miles of oyster habitat in the Hudson-Raritan estuary, and that has been completely eliminated. So here we look at the concept that I was discussing earlier, the textured versus the smooth surfaces, and you can see that our mixes performed fantastically in each scenario, completely covered and encased in these biological organisms. They have 100% coverage, right? But the textured surface promoted a much more, you could say, 3D version or denser populations of these organisms compared to the smooth surface. Now we're going to get into some of our earlier proof of concept and pilot projects. So this is our ecological armor unit, which has been deployed out in Haifa in Israel, in the ports. And ultimately they had these standard protection units that were deployed along the shoreline for years. I think it was over 10 years. And they wanted us to deploy some of our units and see how they fared versus those original units. So right here you see what we call the control antifers, and antifer is just the name of this particular unit itself. And then our ECOncrete antifers, which we developed with the enhanced composition and enhanced textures. So dramatic differences you can see here. And then for every project we've done, since, I have an academic background, the 2 founders of the company are also have PhDs from Tel Aviv University. We do peer-reviewed published papers on all of our projects. So we do 2-year monitoring, ecological and structural monitoring of every project we do. We'll actually go in and scuba dive it ourselves and do these different surveys. So you can see here, again, that the ECOncrete outperformed Portland in every scenario. It even reduced the amount of invasive species, and again, higher abundance. We're always looking at both biodiversity and abundance. We not only want a lot of a species, but we want a lot of different species. It creates a more resilient system. So if you're only attracting or targeting one species, say if you're only trying to attract oysters, and the salinity limit that year because of fresh water or too much snow or too much rain drops below the limit that these oysters can tolerate, the entire population is knocked out. Whereas we typically have 7 to a dozen different species on every one of our projects. This is our seawall project right here. Again, deployed out in Israel. And these are basically, again, a pilot project that were deployed as a temporary installment to evaluate our mixes. You can tell that this has a different texture than the unit you store here. So these are actually subtidal units, so these are completely submerged and autonomous, where these are intertidal units. So these are actually exposed to the intertidal zone, so sometimes they're dry, sometimes they're wet, but ultimately there's different species that populate each zone. So our texture is based off of what we call a target species. We look at the environment, we see which species we want to develop, and the composition and the texture is based off of those species. Like I said, I'll go through these next couple slides pretty quickly because we see the same results. But ultimately, within a 6-month to year time frame, we saw an improvement of biological development, and within a 2-year time frame, in every case, get 100% coverage of the structure. And again, this just speaks to what I just said. Again, we have higher abundance, higher biodiversity in every situation versus the standard Portland concrete. These are our tide pool units, which I briefly mentioned before, and this project is actually up in Brooklyn Bridge Park, and we'll see a little bit more about Brooklyn Bridge Park in a minute. But these tide pool units, they go along a revetment or a riprap shoreline, basically any sort of sloping shoreline that's been protected with stone. And what these units do, as you see in the bottom left picture, they've been placed in what looks like a dry area, right? So they've been placed at the mean high water. So that basically is the highest point water will reach every day. So what they do is they capture water during that period of high water, and then when it's low tide, as you see here, biology can still develop. And these are some of the species that we see. Here it's more algae. Again, now you're dealing with intertidal versus subtidal species. Also in Brooklyn Bridge Park, we did pile encasements. So ultimately you have these timber piles, and you can see in the picture to the top right, at the core of these piles that are supporting piers, and every pier is supported by dozens or hundreds of piles. If you go to Pier 40 in the city, there's over 800 piles underneath it, and they need to be continually encased in concrete to protect the timber. So a couple of years ago at Stevens, I think it was in 2008, during graduation, actually one of the parking lots collapsed into the river, and some of the people that were there to see their kids graduate lost their cars. And what they found was that the timber piles, since the water quality in the Hudson River has improved, a lot of marine organisms, you can see on the bottom right, actually started boring into the timber and weakened it over time. So now we have to continually encase concrete on these timber piles to protect them. And these timber piles actually, in New York, they are driven to bedrock, which is over 180 to 200 feet. So that's why you need that timber pile in the middle, because of course you can't have concrete going all the way down that extreme distance. So what they do is they encase any portion of the timber that is exposed to water in concrete. However, that concrete breaks down over time, ultimately has a lifespan of about 10 to 12 years, and they have to replace it. And this is a multi-million-dollar operation that has to continue at all times. So what we did is we developed special texture and special composition to encourage biology so that we can increase the lifespan of these concrete units so that we can then reduce the overall cost that the city is spending on these pile encasements. But this right here shows you Brooklyn Bridge Park. I would suggest that if you guys have any free time to go over there for sure. It's right by Manhattan and Brooklyn Bridge. So often when we're doing the monitoring, I'll just ride my bike and take the ferry over from Hoboken or Weehawken and just ride my bike over the bridge. And it's one of the most awarded waterfront developments in New York City. So again, if you have any time to go over there, it's just a really beautiful scenery. And you can see loads of different living shoreline projects. But ultimately, they came to us because they wanted structural units, so they wanted these units to perform in a way that they would reduce erosion, protect the shoreline, because that's always their primary function. Then they also wanted us to bring in ecosystem services, ecological uplift. They wanted to basically improve the ecosystem of the park, as well as promote different educational programs for kids. So this, again, just speaks to what I've spoken about as far as ecological pile encasement. So I'll continue past this. I want to make sure we have enough time for questions and discussion. But here are the results we saw. On the bottom left, that was within 3 months post deployment, we had blue crabs mating on the piles, and we had over 60% coverage. Within the 14 months, so just a little over a year, we had 100% coverage, and then compared to the control units, very drastic difference. And again, here are the riprap units which we installed. And what I want you to see here is on the bottom left, that red line is your mean high water, the yellow line is just about your mean low water, and the arrows are pointing to where the tide pools are. So ultimately, this would traditionally be a zone that is completely void of biology because it's too dry. And what we've been able to do is bring a full ecosystem to each one of these tidal pools. So again, I think here we said, yeah, 17 different species were identified. And again, normally this surface would be completely void of biology. So those are some of our early on smaller pilot projects. After Hurricane Sandy, President Barack Obama initiated the Rebuild by Design competition. And ultimately what they decided was that we couldn't repair our system in a piecemeal or patchwork way, right? We couldn't just put up a small wall here 100 feet and something else here and something else there. We needed to start looking at a regional approach, make sure that the damages we saw during Hurricane Sandy wouldn't happen again. So we basically developed a team. Stevens was involved, so I was actually on the team as a Stevens personnel at the time, and then now also ECOncrete was involved, so now I'm still working with the project through ECOncrete. But ultimately we're doing a 2-mile breakwater, and let me see if the next picture shows you. So along with these regional approaches, so basically they funded out of hundreds of different proposals, they decided to fund 6 different projects. And over $800 million was spent on these projects. There's actually one being done in Hoboken, there's one being done in the Meadowlands, so there's one being done on the east side of Manhattan, all along Battery Tunnel, and then on the west side. So there's 6 projects in total, and this project is actually in Staten Island, so it's a 2-mile breakwater, and basically it functions to dissipate wave energy before it reaches the shoreline. So your shoreline is sensitive sediment beach environment. So what we do is basically make this rock barrier offshore that the waves will break on this surface, and then you have basically a calm, quiescent area behind it, which is more favorable for recreation, for biology, and for shoreline stabilization. So this project is actually going to incorporate our tide pool units, our armoring units, and you see along the top we've actually developed our armoring units to cater to different species. So we have developed ones that feed marsh plantains, one to fish, one to oysters. So again, trying to get as many species on site as possible. And it's also important to note that now, basically, the difference in design has come, it's no longer just looking at things from a structural standpoint, an ecological standpoint. Now it's basically this 3-pronged approach of risk reduction, culture, and ecology. And just important to note, because that is the way forward, that's the way things are moving. We were discussing earlier at the beginning of the session that, you can't, now you have to speak to community boards, you have to get all sorts of permissions, and ultimately these are the towns and the cultures that you're affecting, so you should get the input from these people. You should, by creating these structures, improve their life. You should basically, increase their quality of life. And, if you just create a vertical steel bulkhead or some sort of a massive seawall that they can't see the ocean, yeah, we'll protect them. But you know what? That's not really the best answer. And also, too, this idea of redundant designs. Basically, instead of just having one massive seawall or levee, as we saw in New Orleans, if you have one massive structure and that's your only line of defense, if that structure fails, basically that's it. There's nothing else. Whereas in this situation, we have a breakwater, then we have a beach that protects the shoreline, then we have a seawall and dune behind that beach. So there's all sorts, it's 3 or 4 different systems that are being implemented. This is just one of the projects now we're doing. Most of our products to this point have been wet cast, meaning that you make the concrete with a large amount of water. But actually there's technologies, sort of like making a sandcastle, that if you press the sand together hard enough and make it a dense enough mixture, that you can actually limit the amount of water. The advantage of this is that you could produce hundreds, if not thousands of units on a daily basis, compared to wet casting, where it actually has to stay on the mold and dry for a 28-hour period. So that's just, how we're trying to advance and bring our products to be readily available to market. But yeah, I mean, just in conclusion, and this is one of the things that really drew me to this company early on in my research is, urban settings need proper protection from the coastal and marine environments. You're always going to have storms, you're always going to have wave damage, you're always going to have erosion. So we need these systems and these rigid structures to help us. But, we can't, in other portions of the country, they have this, like I said earlier, living shorelines concept where you can use marsh plantings, where you can just use, actual, like, oysters to protect the shoreline. And that's not really the case in an urban environment. So if you go down to Louisiana and the Gulf, you'll see that they're implementing a lot of these smaller living shoreline units that are completely void of structure, completely natural systems. And they work in calm, low wave energy environments, protected environments, but we're looking at urban exposed settings. Ultimately, we need more rigid structures that can perform structurally and also ecologically. And that's all I have, so I think it would be a good time for questions. And again,